Yeah, thanks again for being here. This is the LISST-ABS. If you're not familiar with it, it's a compact and low-cost acoustic backscatter sediment. It's about 2 inches in diameter and a little over a foot long, and it goes for around 4K. So it's as Ola was saying, in that low-cost category, in between the turbidity sensor and the combination of the turbidity and ABS. I'll start with just some essential background on turbidity measurements and use that to develop how we talk about the ABS sensor. Turbidity, I think everybody knows, is the most widely used in situ technology for measuring sediment right now. Turbidity sensors operate on the principle of optical scattering, and the fundamental physics of that optical scattering for sediments indicate that the turbidity measurement really depends on the particle cross-sectional area, not the particle volume. For example, if we have a suspension of different particle sizes, the turbidity that we get out of the sensor will be proportional to the sum of the cross-sectional areas of the different particle sizes. So the total area of size 1, the total area of size 2, total area of size 3, and so on. And then we can also think of that cross-sectional area as the ratio of particle volume to particle size. So then in that case, the turbidity becomes, you can think of it as proportional to the sum of volume over size for size 1, volume over size for size 2, and so on. And just considering that, it follows that from the basic physics that the turbidity sensors will respond to concentration of particles of different sizes differently. If we assume that we have some particle density and then consider that the volume in that equation is proportional to the concentration, the mass concentration, then the output of the turbidity probe that you get, for example, in volts, its sensitivity to actual mass concentration will decrease for increasing particle size. So, for example, if we consider the same mass concentration of, say, 1 milligram per liter of 200 micron sand and 10 micron fines, then the turbidity probe output for the larger 200 micron particles is 20 times lower than that for the 10 micron particles. This is another way of looking at that, but with actual data. This is a plot of laboratory analysis of total suspended mass concentration and the corresponding NTU measurements from a turbidity probe for a variety of sediments in different sizes. This is from Bundgaard et al. In 2019. The axes are very difficult to read on the slide, but the y-axis is the measured TSM concentration, and the x-axis is the response of the turbidity sensor in NTU. There you can see that there's different lines here, different lines that have been fit to points, and each of those different lines and sets of points are different sediment sizes. So here you can see the arrows pointing to a line that shows the fit between TSM and NTU for, in this case, 100 micron sediments. And you can see that it's very steep. So that means that it takes a large increase in sediment concentration to cause a small increase in turbidity. The second arrow here, I've just highlighted the 140 milligram per liter TSM concentration on the y-axis. And if we go horizontally across until we intersect that line, then vertically down, we see that that corresponds to roughly 5 NTU. So 5 NTU corresponds to 140 milligrams per liter for those 100 micron particles. Next, we can see this line on the lower part of the plot that indicates the correlation between TSM and NTU for 5 micron particles. And you can see that that's much flatter than the other curve. So that implies that a small increase in sediment concentration causes a large increase in turbidity, or NTU. If we then look over at 7 milligrams per liter on the y-axis and then go horizontally across to where that intersects the 5 micron particle line, you can see that it corresponds to also 140 milligrams. So it corresponds to 7, where I had the line. And then that also corresponds to 140 milligrams per liter for the 100 micron particles. So just to pull that together without the arrows and the dashed lines, 5 NTU for 5 micron particles corresponds to 7 milligrams per liter of actual concentration. and 5 NTUs of 100 micron particles corresponds to a concentration of 140 milligrams per liter. So this is just a real example of those 100 micron particles are 20 times larger than 5 micron particles, and the 140 milligrams is 20 times larger than 7 milligrams per liter. So you need a lot of large particles to create the same turbidity as fine particles. In essence, that means that large grains are not seen by turbidity sensors in the same way. And the LISST-ABS really was designed to deal with this issue. To explain how the ABS addresses that, how the ABS works, and why it's fundamentally different in capability compared to a turbidity sensor, we really need to look at some of the basic physics behind how sound and light scatter off particles. In this figure, on the y-axis, what we have is scattering, whether it's optical or acoustic, the scattering intensity per unit volume of particles. So think of that like scattering intensity per mass. On the x-axis, there's a quantity called Ka, or the wave number, and we'll explain that in more detail in the next few slides. But for now, the key thing to pay attention to is the shape of this curve. For low values of Ka, or the wave number, the scattering intensity per unit volume increases linearly up to a wave number around 1, about 1/2 to 1. Then it flattens out and the scattering intensity is roughly constant or a little wavy until the wave number gets to around 10. And then beyond there, the wave number increases and the scattering intensity decreases linearly again. As far as describing discussing the wave number, or Ka, K is really I think we call it the frequency wave number, and that's just a property of wave. Lambda here is the wavelength, F is the frequency, and C is the speed of the wave. You can see here K, you can think about it in terms of both the wavelength of the wave or the frequency relative to the speed of the wave. If we then think of this other quantity, Ka, that's the wave number times the particle radius. So this is key to the interaction of the wave with a particle. This is now a function of the wavelength or frequency as well as the particle size. So that very simply, Ka is now 2 pi A over lambda, or 2 pi Fa over C. And another way to think of this is that for an instrument with a fixed wavelength or fixed frequency, Ka is an indicator of particle size. For example, if you have a 1200 kilohertz ADCP or a turbidity sensor measuring at 850 nanometers wavelength, for that given sensor, the Ka will change with particle size. There's a couple other concepts related to the wave number and Ka that are important. We often talk about the Rayleigh limit, which is where Ka is less than around 1. That's that first linear region. In this case, the scattering per concentration increases as the cube of Ka, or frequency. And another important aspect here is that we use scattering at 2 different frequencies. For example, the ratio of frequency 1 to frequency 2, then there's no dependence of that ratio on size. A quick takeaway here is that in Rayleigh scattering, multi-frequency or multi-wavelength approaches don't add any information about size. Because the wave number is a function of particle size and wavelength or frequency, we can express the entire curve as a function of particle size only if we fix the frequency or wavelength. So in this plot here, that's what we've done for the different curves. The different curves are a range of frequencies typical for ADCPs, so 75, 300, and 1200 kilohertz, and then also the LISST-ABS frequency of 8 megahertz, and a hypothetical 3 megahertz sensor. And each of those curves, we have computed the scattering intensity as a function of particle size. The thin vertical lines you can see on the 1200, 300, 1200 kilohertz, 3 megahertz, and 8 megahertz curves show where the wave number Ka is 1 for that particular frequency. So this is around where the curve starts to flatten and become wavy, so you're out of the Rayleigh regime. For the 75 and 300 kilohertz sensor, the scattering varies with grain size up to a grain size of around 6 and 1.6 millimeters, so off the plot. For the 1200 kilohertz sensor, the scattering varies with grain size up to around 400 microns. You can see for the magenta curve, that's the LISST-ABS frequency, Scattering varies with grain size up to around 60 microns, and then beyond that, it's almost only concentration that will cause variation in the ABS signal because it's not depending on particle size. With the 8 megahertz transducer of the LISST-ABS, you could think of that as being best for suspended sediment concentrations or measuring concentration for particles above 60 micron. Because the other sensors are sensitive to variation in both particle size and concentration, they're below the Rayleigh limit. It requires a lot of work to use their signal for SSC. So that's where you get into individual calibrations for individual sediment sizes. Another way of thinking about all this is that Sequoia's philosophy on this instrument is that when you're looking at how suitable a particular surrogate technology is for measuring suspended sediment concentration, use the fundamental physics to guide you and select the technology. So that's the impetus behind the LISST-ABS. In this case, we selected a frequency where changes in size versus concentration cause as little change to the signal as possible. Coming back to the idea of the regimes in this scattering curve, we can identify 3 different regimes. So we talked briefly about the Rayleigh regime, where Ka is less than 1. Scattering here changes strongly with grain size. Increasing grain size leads to increased scattering. This is where most ADCPs are working. Then there's a transition regime around Ka of 1. In this regime, scattering varies only weakly with grain size and kind of in a strange way. Increasing size here doesn't really change scattering significantly. There's just a little bit of waviness. This is where the LISST-ABS is operating. And then there's a so-called geometric regime where Ka is greater than 1. In this regime, scattering also changes strongly with grain size, but in this case, increasing size leads to decreased scattering. So this is where turbidity or optical sensors are working. Remember that we said earlier for a particular frequency that Ka varies only with size because the frequency is fixed. We can select a wavelength typical for turbidity sensors and the wavelength used for the ABS, and then we can recompute this figure purely as a function of particle size, and then we arrive here. So recall again that the idea of the wave number Ka and the 3 scattering regime applies to both turbidity and acoustics. So it's the same fundamental physics. What we see on this figure is 2 curves. One is blue and one is green, and they're crossing each other. The green curve is computed for the operating frequency of the LISST-ABS, and the blue curve is computed for the operating frequency, or typically we say wavelength, of the turbidity sensor. Because we now have fixed the frequency in both of these cases, the curves are functions of particle size only. So what we see now is that how turbidity, the blue curve, decreases with increasing grain size, and how the LISST-ABS, the green curve, has a constant output for size larger than around 60 microns. Below 60 microns, the ABS output decreases with decreasing size. So bringing this back up here, it's very important to realize that this plot with the blue and green curves is the same figure we saw in the previous slide. We're just looking at different regimes of that curve for different frequencies or wavelengths. So we can plot that scattering intensity only as a function of particle size. This is why just the general idea of the blue and the green curves is a comparison of why the LISST-ABS operating in the transition regime is better than a turbidity sensor operating in the geometric regime, because the ABS in that transition region has very little change in the signal as particle size changes. Only change in concentration will cause a change to the scattering signal. There's one other issue that we need to address. We've kind of been roughly equivalent with volume and mass, just assuming that we can connect the two with a particle density. And typically we'd think convert from volume to mass with 2.65 grams per cubic centimeter. When we actually compute the scattering intensity as a function of Ka or size, it's the scattering per unit volume that is computed. So in order to compute this to scattering per unit mass, it's necessary to assume a density. The physical theory behind this is capable of dealing with the volume, and then you use whatever density you want to put in. The effective mass density is perfectly well known in the sound scattering models, but we don't have any experience with it, or we haven't seen papers addressing it for practical applications, especially where it refers to a non-solid particle density. All of the ABS data that we produce is interpreted as equivalent unflocculated solids. In other words, assuming a mass density of 2.65 grams per centimeter cubed. In this sense, it's no different than a turbidity sensor. You typically calibrate a turbidity sensor for field use with water samples that you would take from the field. And you really don't know in that case if the particles are flocculated or not. So you don't know what the turbidity signal is responding to, whether it's flocculated or unflocculated particles. You simply use whatever output the turbidity sensor gives you in volts or NTU at the time the water sample was taken, and you use that for your regression. Then you assume that the particle size and state, flocculated or not, or the degree of flocculation, doesn't change at all going forward until the next time you take a set of water samples and make a new regression. You might not know that that's what you're assuming, but you do assume that with the particle size and state stays the same when you perform a lab calibration in this manner, or even an in situ calibration. So that's pretty much the theory of the ABS. We'll talk a little bit about the design and how you develop an instrument that takes advantage of the acoustical physics of the megahertz transducer versus a turbidity sensor. Here's some quick specifics about the way the LISST-ABS actually measures acoustic backscattering. The LISST-ABS uses, as we said, a transducer of 8 megahertz and sends out a 26 microsecond pulse that is about 5 centimeters long by the time we actually look at the received signal. The sampling volume of the instrument is in front of the sensor out to about 5 centimeters. After another 26 microseconds, the start of the sampling volume is 10 centimeters away from the transducer, and the end of the sampling volume is 5 centimeters away from the transducer. Now we start to listen, and after yet another 26 microseconds, we start to get the echo from the particles that were 5 centimeters away. After yet another 26 microseconds, we detect the return echo from the particles that were 10 centimeters away. After 73 microseconds, we've detected all echoes from within the sample volume. This is the basic way that all monostatic acoustic scattering sensors work. One key here is we use a short acoustic path length so that we don't have to deal with attenuation due to water over that path length. We do a fair amount of averaging within the actual instrument firmware. Like I said, the sound attenuation due to water is minimized, but in high concentrations, we still apply a correction for sediment attenuation that we'll describe next. This plot shows backscattering profiles for a concentration series of 5 to 10 micron sorted Arizona test dust. On the x-axis is sample number of the received backscattering acoustic energy after all of the internal processing. Here you could also think of the sample number as the distance or range from the transducer. The y-axis is the magnitude of the received backscattering in logarithmic units. And each of the different curves, increasing from the bottom of the plot towards the top, is a different concentration, ranging from no sediment added to 60 grams per liter. Close to the transducer, you can see there's flattening of the response. That's due to near-field effects that we won't talk about here. But you can see for a wide range of concentrations that beyond sample number 20, the slope of the profiles are constant for concentrations less than around 3 grams per liter. So we'll call that slope 1, slope S1. For higher concentrations greater than 3 grams per liter, you can clearly see that the slope is changed. So we're calling that slope here slope S2. Attenuation due to water, or more likely the geometry of the beam, haven't changed in those two cases. So this difference in slope is due to the attenuation by particles. Again, slope S1 is the case of negligible particle attenuation, while S2 is affected by particle attenuation. Essentially, we use the difference between these two slopes to correct for particle attenuation. This allows the LISST-ABS to work across a much wider range of sediment concentrations. In essence, the LISST-ABS is just a ceramic transducer and a whole bunch of electronics. That's it. In practice, there's a lot of considerations that have to be taken into account for the transducer. It has to be thin because it's operating at 8 megahertz, and because it's thin, it's easily breakable if subjected to too high of a water pressure. So the current depth rating is 100 meters. Other instruments like ADCPs that operate deeper are typically operating at lower frequencies, so they use a larger transducer, which is easier mechanically to make it resist the high pressures. The transducer is also made of ceramic. That's porous, so it has to be coated to seal it from the water and protect it. The ceramics are brittle. There's a lot of considerations when we apply the coating, because the thickness of the coating should be a fraction of the wavelength. Otherwise, the signal isn't transmitted properly through the coating. There's a few hundred ABSs out there, and we have a fairly good idea of the robustness of the coating and the transducer setup. We've not had any reports of abrasion on the coating. For example, when using the LISST-ABS in very high concentration environments like a hydropower plant, we've not seen issues. We've had a few instruments come back for repair after being hit by river debris like trees, but in general, that's just bad luck, and probably any sensor would have an issue if it gets hit by a tree. We won't go into the electronics in detail here. The electronics on a turbidity sensor aren't trivial when you're dealing with the small analog signals and ambient light, but suffice it to say that the electronics associated with driving an acoustic transducer and dealing with the time gating of the response and averaging at very high rates makes the electronics much more complex in the ABS compared to a turbidity sensor. I think I'm turning it over to Ola.
Yeah, thanks, Wayne. Moving on in the ABS presentation. So just to sum up, how does it actually differ from what is out there today from turbidity sensors? And as we've hopefully explained, because of this region where the relative sensitivity of the sensor to changes in particle size is more or less constant and only changes with changes in concentration, then it's minimally influenced by changes in particle size. Again, it's the green curve you see versus the blue curve, and the red arrow shows this region, this transition regime that Wayne has been described, where we have this fairly constant output from the sensor regardless of grain size. So it's minimally influenced by changes in particle size, and it obviously handles fouling better simply because it is acoustics. We have seen data which we haven't actually been able to show from yet deployments in estuaries, where the ABS has been deployed together with turbidity sensors over a period of months. The turbidity sensor fouled 2 or 3 times in that period, and the ABS didn't foul at all and just kept plugging along, giving good data all the way through that deployment, where the turbidity sensor had to be maintained several times and cleaned several times. We are working on seeing if we can get some more data from some of our customers on that. And in that case, we'll be happy to share it, of course, on our website. It does indicate that in general, it does handle fouling better. And that is also why ADCPs, for example, are so popular, because they also handle fouling very good for long-term deployments for current velocity measurements, for example. Where the ABS doesn't differ a whole lot from a turbidity sensor is the price. Of course, there are extremely cheap turbidity sensors, but it's roughly at $4,000. It's roughly in the same price range. The main difference is, just to sum that up very quickly, is that the ABS is as minimally influenced by changes in particle size as the physics will allow. Of course, there's always electronics design considerations, so of course there's some limitations imposed by that as well. As Wayne said, we are really trying to understand the underlying physics and then design the instruments based on the actual physics and what that will allow in terms of measurements. And then we move on to how we connect to it and how we output it. And the overarching design philosophy behind the ABS, it has always been that aside from the electronics, which is so complex, we won't really get into that today, then it should be made as simple as possible so that it could be as cheap as possible. And for this reason, we don't offer any internal power or logging capability. And as we'll see in a little while in some of the subsequent slides, then there are so many other options for logging and power that already exists that it doesn't really make sense for us to think about that, because they are readily available off the shelf from a number of suppliers. So it's really not necessary for the ABS to have its own power or logging or memory. So in order to actually power it up, it just needs 10 to 18 volt external power. And any data logger for environmental use can communicate with SDI-12 for analog or RS-232. That'll do the trick. I know that the USGS are all very familiar with the SDI-12. We have some customers who prefer analog for a number of reasons, and then there are others that use RS-232. RS-232 is used a lot in ocean science applications, whereas SDR12 I think is used a lot more in environmental applications. So we have Campbell Scientific, which I assume everybody knows, and Fundrest, which I think some of you also know. They have quite a bit of experience with the ABS. We've sold multiple ABSs to Campbell that they have integrated into various systems where they sold the entire system to their customer. The same goes for Fundrest. So we have a good collaboration with both of them. It's formalized a bit more with Fundrest, who is actually an actual distributor of the ABS and the AOBS here in the US. So you can buy the instruments directly from Sequoia, you can buy them directly from Fundrest. The price is the same. And Fundrest even have them on their web shop, so you can check them out instantly with a credit card as well. And we know that Fundrest has performed quite a bit of system integration services as well for some of their customers with the ABS and the AOBS. We have a cable for handling these three different outputs, the SDR12 analog RS-232. It's being output continuously by the ABS. But in order not to have three different cables, one for each, then we have a standard cable, and then we have a little Molex connector on the end of that. And then we provide three small pigtails that are each wired up for SDR12 analog RS-232. So if you have your ABS connected to a data logger, for example, an SDR12 data logger, and then it suddenly breaks down, and the only thing you have in your toolbox is an RS-232 data logger, then you can just plug that in. And then the only thing you have to do is disconnect a little Molex pigtail. That's the one you see in the picture on the right. Unplug the SDR12 pigtail, and then plug in the RS-232 pigtail to the cable that connects to the ABS, and then attach it to your terminals on your RS-232 data logger, and then you're in business again to switch between different data loggers just by switching that little pigtail with a Molex connector. So the output of the ABS, and we've been thinking a lot about how that should actually be phrased, and I think that is still developing to some extent. So the output is what we call standardized because, and you'll see this when we get to the calibration section of this talk later this morning or afternoon. We calibrate the ABS in the lab using some 75 to 90 micron glass spheres because they're readily available and we know how to handle them and keep them well mixed and suspended, so we have a homogeneous suspension when we test and calibrate our instruments in the lab before they go out. We standardize the concentration, if you like, to these 75 to 90 micron glass spheres. So if you were in an environment where the sediment size was always 75 to 90 micron, then the LISST-ABS would always output the exact accurate concentration of the suspended particles. Now, we all know that it's not 75 to 90 micron constant anywhere. It varies quite a bit. But if you follow the red arrow on the figure, remember we are here in the transition regime, and you can see 75 to 90 micron particle size changes from 75 to 90 to maybe 100, 150 micron. Then the relative signal changes tenths of percent. So it's really not a whole lot compared to how much the turbidity signal would change. If you had calibrated a turbidity sensor using 75 to 90 micron particles, that would change sometimes hundreds of percent and multiple orders of magnitudes. But across this transition regime, the concentration or the output signal from the ABS doesn't change a lot, except, as I said, tenths of percent around an average value when we use the 75 to 90 micron as our standard particles for calibrating the concentration output from the ABS. So that's what we mean when we say standardized concentration. I hope it's fairly clear from just looking at these two that the signal is a lot more stable for particles larger than 60 micron than a turbidity sensor can ever be, regardless of how much you actually calibrate it. And if not, then we'll take that during the questions for sure. So we have the analog output. That is, of course, that's an output in voltage. And because we have a very wide dynamic range in the concentration that the ABS can measure, Wayne showed measurements up to, I think it was 30 or 60 gram per liters. Then the analog output is the logarithmic of the concentration. So if you have an analog sensor and you're logging the analog signal, then you have to do a little bit of math just to convert that voltage into an actual concentration afterwards. However, if you're using an SDR12 or an RS-232 data logger, then the output you get is the standardized concentration directly. For example, 1,200 milligrams per liter, with no further computations or nothing else have to be done. So how well does it actually work? Probably the next question people would have after all this talk about physics and design and theory. So here's some example that Tim Stroud and others have granted us permission to use. This is from a report that's being published right now, as far as I know. Tim can probably comment on that later on. But we have been given permission to use some of these data in this presentation, and there's a number of measurements here from a number of rivers and streams across the country, from Elwha River up here in Washington and to Missouri River, Rio Grande, Colorado River, Sacramento, and also in the Midwest. And you can see there's been a number of observations in each of these rivers and streams. On all those locations, the ABS and the turbidity sensor and actual physical samples were all co-located. And then a range of correlation coefficients were computed between the ABS and the suspended sediment concentration, and between the turbidity and the suspended sediment concentration. And if you look at the two columns to the right, which shows the correlation coefficient between the ABS and suspended sediment and turbidity and suspended sediment, and you can see the ABS does a pretty good job with correlation coefficients mostly above 0.8, except in one case, Sacramento River. And you can see turbidity is varying. The correlation coefficient for the turbidity sensor and suspended sediment concentration varies between 0.1 to 0.9. So there's a lot more variation in the correlation coefficient between turbidity and suspended sediment than between the ABS and suspended sediment, which is generally higher and better. And another way of looking at that is this plot, and that shows all the data. On the x-axis, we have the concentration as it comes straight out of the ABS. So simply just plugged into a data logger, and then the concentration that comes right out of it. And it's plotted against, on the y-axis, the actual suspended sediment concentration from water samples. And the dotted line is the one-to-one line. So if all the data were completely in agreement, then all the data points would fall on the dotted line. And you can see that in general, at least for concentrations above about 100 milligrams per liters, then the data are actually fairly close to the one-to-one line. For concentrations that are below 100 milligrams per liters, then the ABS tends to underestimate the concentration a little bit. And that's not really extremely surprising, because in rivers, when you have relatively low concentration, you also often don't have very large particles because you require some current and some flow in order to keep large particles suspended. So what you have left at low concentrations is really mostly the wash load, which the turbidity sensor is better at seeing instead of the ABS, because the turbidity reacts better to fine particles, whereas the acoustic backscatter sensor reacts better to the larger particles. Here's another plot from that same report that shows some data from the Missouri River. Out on the far left, we have all the turbidity data from 5 verticals across the river, from the left bank to the right bank. And you can see all the turbidity data with the dotted lines. They all fall more or less on the same value and with very little vertical variation. If you look at the ABS data, and you can see there's a pronounced vertical variation with much higher concentration as we are going down the profile towards the bed where we have sediment being resuspended by the current. And you can see there's 2 ABS profiles in between, the ones that is vertical 1, which is close to the left bank, and then the profile marked with a little triangle, which is close to the right bank. And they're sort of in between. And that's because here we have currents that are slowing down, as opposed to the center of the river where we have the fastest flowing currents. As we're getting closer to the banks of the river, then the current slows down. So the suspended sediment starts to settle out and wash load starts to dominate. And that's why we see a decrease here in the ABS. We also see that we don't really get the same vertical profile. It's more or less straight down like the turbidity sensors. That's just to give you an example of how well the ABS actually works. One thing you should be careful about is you shouldn't just see how well it tracks turbidity data. If the ABS tracks an OBS or any other turbidity sensor all the time, then there's really no reason for it. But it's because turbidity is sensitive to the same scattering as we see with our eyes. So if water looks turbid, it will seem as turbid water on a turbidity sensor, but an ABS in that same water might rate near 0 because there's no large particles suspended. So how about accuracy and precision? We don't have any specific value for the accuracy of the ABS, except if we come back to the curves we've shown numerous times before that shows the scattering intensity as a function of particle size. Remember, in what we call a transition regime, it's flat-ish and a little wavy. So in that region, we are around 30%, give or take a bit, of the actual value, regardless of the grain size. If you look at these figures, that explains the difference between accuracy and precision, and look at where the ABS would fall. Then if you start at the bottom right plot with the figure that shows high accuracy and high precision, that's what all sensors and instruments aspire to, hit that bullseye. So you always get as much accuracy and precision as you possibly can get. No sensor is really getting there. This, for example, when you're talking suspended sediment, this would typically be a water sample analyzed by a very experienced laboratory technician who could always get the actual accuracy and precision. If we go up and look at the top right plot with low accuracy and high precision, then we can see that all the data points are all clustered together. So they're all at high precision, but they have fairly low accuracy because they are far away from the actual target. So if you stay in the laboratory technician terminology, this could be, for example, if it's a technician that's used to always filter 1 liter, and then suddenly that technician gets a lot of water samples that are 2 liters, but they forget that when they actually have to compute the concentration, so they divide by 1 liter instead of 2, then all the data points will still cluster together because the technician is still just as good, but the accuracy is low because they have the volume wrong. But crucially, when you have a low accuracy and high precision, you can always adjust it. You can see all those points could be adjusted right into the target, into the bullseye, just by one transformation. It's much worse if you have a sensor that's low accuracy and low precision. So that's the top left plot. That's really completely useless because you can't really use it for anything. And then we have a sensor in the bottom left plot that's high accuracy and low precision. So it's generally hitting the target most of the time, but not all the time. And that's really where the ABS is, as long as the particles are larger than 60-ish microns, as we've seen. And you might see that the 20, 30, 40% variation around a true concentration seems like a lot, but you do have to contrast that with turbidity sensors, who varies a lot more around the true concentration. So a turbidity sensor would really be somewhere in between the high accuracy and low precision and typically the low accuracy and low precision, moving up towards that on a line, depending on how well it's calibrated and how much the particle size has changed since the calibration. But the bottom line is that if somebody is already using turbidity sensors, then the ABS will certainly have at least the same accuracy as the turbidity sensor has. And in a lot of cases, it can be up to a factor of 10 better. That's really the essence here. So just to sum all of that up, fundamentally, the acoustic backscatter sensor has better agreement with suspended sediment than turbidity has with suspended sediment, as it should have according to the physics that we've presented. And the deviations that we see, and which we've also seen from other customers, that's really mostly due to fines where the ABS loses sensitivity and turbidity can perform better. And again, that's also completely as according to physics and as expected. So in general, it really works fantastically well for suspended sediments, suspended loads. And with that, we have actually arrived at our first Q&A.